I'm Ignacio Neumann. I'm a great methodologist. I'm an internist by training. I have no financial conflict of interest. I'm a member of a great working group. I invite you to following in our LinkedIn profile, which has become the main way to communicate great news about grade and publication and tools. Also, you can visit the Grade book. Here, the official source of grade, we are updating the Grade book, and we may not finish 2026, but we are in the process until I think we will finish 2027. But the certainty assessment, which is what you do in Cochrane, is already everything is updated. Okay, so we have had some sessions about the certainty of the evidence. We have an introductory session, result bias. We also have about how to assess designation bias. And now the turn is for inconsistency and imprecision. And then there is one extra session about indirectness. So, and this will complete the series. So the certainty of the evidence, this is the definition, is the confidence that the true value of an estimate falls into a specific range. It sounds complicated, but it's actually very simple. For example, if we have the pool estimate in a range we defined previously as moderate benefit, the certainty of the evidence is our confidence that the effect of the intervention is indeed a moderate benefit. And this is an important departure from previous definitions of the certainty of the evidence. The previous definition before 2017 was that our confidence that the true values flow to the point estimate. So, for example, the point estimate was a relative risk of 0.8, or confidence that the true effect was a relative risk 0.8. But nowadays, we say, well, first, we need to rate the certainty of the absolute effect rather than the relative effect. And second, we are not so interested in whether it's 0.8 or 0.9, or whether the relative risk is a reduction of 50 or 51 per thousand. So if we consider this as a moderate benefit, what is our confidence that it's indeed a moderate benefit? It's a more range, it's a more practical and pragmatical definition. So high certainty, this is the logical conclusion of the definition. High certainty means that we have high certainty that the true value is in the range of interest. So, another way, if we believe that we are rating the certainty on a moderate benefit, high certainty means we are very confident that the effect of the intervention is a moderate benefit. Moderate certainties were less certain. So again, if for this example, we keep rating the certainty in a moderate benefit. But for example, if the certainty is moderate, it means, well, we are not sure if moderate anymore, it could be small. So we believe that the effect is more moderate. And you see that the lower the certainty, the less confident we know where the true effect is. So in this case, for example, low certainty may means that the true value may deviate from the target. For example, could be trivial, small, or moderate if we are rating the certain. And very low means we are really have very little information about to judge where the true value is, and may depart significantly from what we target. In a way, if we're rating the certainty to a moderate benefit, very low certainty, we say, well, we're not sure it's moderate, it could be trivial, it could be even a small harm. So in the Grade book, and we have structured the certainty assessment in these 4 steps. So first, we need to determine the threshold, because now rating the certainties is in the relation to a threshold. If you change your threshold, you will have a different certainty rating. So the certainty rating is not a property of the evidence itself, it's a property of the evidence and the threshold you choose to assess this evidence. And we can argue that this threshold always has existed. Now, the only thing we're saying is you have to be explicit about it. Then you say, okay, what are you determining the certainty on this? Moderate benefit, small benefit, non-trivial effect. So to be clear about that, then you evaluate the evidence, and then you decide whether to rate down or up. And this is an important distinction. Now, the what you say, well, I look at the evidence and I decide where to rate down. Those are different steps and need to be, and we will talk about this. So this is the great approach. This is a great figure by Carlos Cuellar. And this is so the assessment is start with the study design, which is a kind of a legacy from the levels of evidence. We had randomized trial in start as high certainty evidence, but there are 5 domains that may decrease the certainty of the evidence. One thing is to assess the limitation. Another different thing is to decide whether to rate down. And we need to separate those processes. And we talk a lot about this in risk of bias, and Holger will talk about this about in indirectness as well. But today we're going to talk about imprecision. And imprecision is a very special domain. It is the only domain in gray that measure or captures random error. So if you go to all the 5 domains of gray, 4 of them capture systematic error, bias. This is the study limitation, indirectness, inconsistency, and designation bias. Imprecision is the only domain that captures random error. And the primary way to assess imprecision is the confidence interval. There is some scenarios where you need to assess the review information size. They are limited to scenarios where you have a large effect or trivial effect, but for most of the time with the confidence interval, you will be fine. The good thing about random error, we have very good way to measure it. So how do we capture measure random error in a meta-analysis of randomized studies? Through the confidence interval, which reflect where the range of plausible values are. So the confidence interval tells you the range where we believe the true value is. And the good thing is over the confidence interval, there is a normal distribution. So it's a probabilistic distribution. So if we go back to say, well, we are assessing the certainty in relation to threshold, for example, at the top of the figure, you have an intervention that shows trivial or no important effect. And you see that the confidence interval, the 95% confidence interval, is entirely with the trivial no important effect. So we can say that there is no range within this 90% probability. There is no value that is outside the trivial or non-important effect. So we're very sure that the effect of intervention is trivial or not important. So a way to conceptualize this or to see whether we're making the right call is imagine yourself on one extreme and the other extreme of the confidence interval. If you are in the same range, then you don't have issues with imprecision. The second, you say, well, one extreme of the confidence interval is in the trivial no effect, but the other extreme is just a small effect. So now, if we only consider random error, we are not sure whether the true effect of the intervention is actually a small effect or a trivial or not important. Then, since we are where we believe that the true effect may be in these 2 ranges, and we'll go back to our definition, this match or rating down one level of the certainty of the evidence. And then you can see the logic that, for example, in the third scenario, from top to bottom, the one extreme is in trivial no effect, the other extreme is in a moderate effect. So we are not sure whether the effect is moderate, small, or trivial. So in a way, we have less confidence about where the true value is, and then we should rate down for 2 levels. So a practical way of measuring precision is you define your threshold. Every time that the confidence interval crosses a threshold, you rate down by 1 level. And I think this is a very nice way to set the certainty of the analysis because it's very yes or no. There is, you don't need to this is something that you can automatize, you can audit. It's a very, 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 in a way, objective way. The only thing you need to set your thresholds. One important consideration about this is if you look at the third and fourth estimates, those are statistically significant difference, right? Because they do not cross the no effect. But those 2 are the one we're penalizing more by imprecision. Yeah, I think the third level, the bottom, the figure should cross another, the additional threshold is crossing only two, it should cross three thresholds, because that will make the figure more clear. Yeah, we need to correct that. But so notice that years ago, the imprecision was judged to the no effect line. But now the no effect really doesn't mean anything, because no effect means that there is any difference will do. And we know that in real life and clinical practice, not any difference will do. We require a minimal meaningful difference. Otherwise, the intervention, you may detect difference that are statistically significant, but are not meaningful. So the no effect line is not a relevant threshold generally. And so crossing the no effect line doesn't mean anything really in our current conceptualization. And really, we should look at the threshold being crossed, but then small trivial effect, moderate or large effect. So this is imprecision is a very kind of a straightforward, because it's random error. We have good ways to measure random errors, and good way to represent random errors, and we only need to see whether the confidence interval cross the confidence interval. Inconsistency, and we will see in a minute or in some minutes why we are covering this together, is also something that you can deduce from the meta-analysis, just like random error, but this is a systematic error. We believe mostly a systematic error. And inconsistency evaluates whether there is substantial difference across the different studies. So the logic is, if all the studies say the same, then we are more confident that if the studies give you different answers. And for many years, the primary way to assess inconsistency has been the visual inspection of the forest plot. The problem with this is we said you need to visually inspect the forest plot, but we didn't tell you how, right? So just look at it. Now we have better rules. And also some statistic like the Cochrane test on the I-square. But we will see now that over the years, and this has been a learning process, we have realized that the statistical tool, as always, may measure statistical things, not necessarily meaningful effects. Something could be statistically significant, but not meaningful. In the same way, you can detect statistical heterogeneity, which is not meaningful. And now we have a better way to assess this. So this is what we meant by look at the forest plot. So typically we say, well, if the confidence interval overlap, the point estimate are close to each other, we typically say, well, there is no significant inconsistency. Inconsistency arises, for example, when the confidence interval do not overlap and when the point estimate were far apart. But one of the difficult things was, okay, why do you mean by far apart? How do you measure this? It's the same way. How do you assess whether the confidence interval is wide or narrow? So that was in there, right? In there, we didn't have rules for that. But now we say, well, we now have, with threshold, we have a very good way to do it. And this is a key figure of the presentation. And this is the same meta-analysis, the same for study, the same pool estimate. But in so in the left, we have inconsistency, and in the right, we have no inconsistency. And why is this? It's because in the left, we have two studies suggesting a small effect and two studies suggesting a trivial effect. If you go to the rules, we say the confidence interval do not overlap, which is a problem, but the point estimates are in different ranges. And this is the key part, right? The point estimates are in different ranges. So one set of studies saying no important effect, another set of studies is saying small effect. And well, we have serious inconsistency. In the second panel, we have the same analysis, but now, although the confidence interval do not overlap, all the point estimates suggest no important effect. So it's about all the studies give you the same answer. And notice that whether they're telling you the same answer or different answers is in relation to thresholds. It's not a property of the study themselves. And if you go to the I-square and the Cochrane test, the I-square is 99% in both cases, and the p-value is significant in both cases. So what does it mean? It means that the I-square detects statistical heterogeneity. So a practical way, if you have an I-square of 0, then generally there is no statistical heterogeneity, probably no inconsistency. It's almost impossible to have inconsistency with I-square of 0%. But if you have an I-square that is different from 0%, and even if it's like 10%, 50%, there is no meaningful threshold for the I-square. There's some statistical heterogeneity, but it's important to judge whether this statistical heterogeneity is meaningful, because in this example, you have both I-square is 99%. In one case, it's meaningful because you don't know whether the effect is small or trivial. In another case, it's not meaningful. All the studies suggest no important effect. You are only seeing a statistical inconsistency, no meaningful inconsistency. So one of the concepts we have realized over the years is I-square could be positive. We have very precise estimates, but that necessarily means that you are seeing inconsistent result. So in a way, be aware of the I-square. When it's 0, very helpful. When it's different from 0, you need to check. And how do you check your forest plot? You need to check the overlap between the confidence interval and the distance of the point estimates. And how do you check the distance of the point estimate? Rather than eyeballing, it's better to do it in relation to threshold. So this is what you will find on the gray book, and how to judge inconsistency, how to judge imprecision. This is a standard gray knowledge, and now we are going to move to a more conceptually challenging concepts, and hopefully, I hope you understand why we're doing this session together. So, and this is an old story, but in a meta-analysis, we have two sources of variability, or variation. One is random error, which maps to imprecision. But also we have between study variation, difference between the point estimates. We measure with a variable called tau square, and this maps to inconsistency. So random error, standard error, imprecision, tau square, inconsistency, different sources of variability. If we are very strict, only the fixed effect model calculate the confidence interval using random error. If you use random error, your confidence interval already is considering some of the between study variation. There is different school of thought. I'm from the school of thought we generally use random effect models, that very, very few exceptions. So when you're using a random effect model, you are not longer only evaluating imprecision, because the confidence interval you are using also contain a variable related with between study variation, which conceptually is inconsistency. So you see that fixed effect model, the confidence interval is entirely random error. Random effect model, you have random error and a small part of between study variation. So when you're using a random error, by definition, you're not assessing only imprecision. You're assessing imprecision and some inconsistency. So this is a key distinction, and that is why if you are like us and you use typically random error, you're typically assessing with the confidence interval imprecision and inconsistency simultaneously. But we now have a new tool in the Cochrane in REMA, which is the prediction interval. And the prediction interval, if you look at the formula, is very similar to the random effect confidence interval, but now tau square is added to the final interval. So if you conceptualize this fixed effect model is really imprecision. The only thing that is measuring imprecision is fixed effect model. If you move to random, you start to consider inconsistency. And if you move to prediction interval, then you are fully considering consistency. But when you have a prediction interval, you're considering simultaneously inconsistency and imprecision, because the way the prediction interval is calculated is random error plus between study variation. So what does this mean? If you have tau square of 0, so no tau square of 0, I square of 0, no suspect of inconsistency, the fixed effect model, the random effect model, and the prediction of the interval should all match. So you are the same interval. You don't have to worry. That's why I square of 0, you don't have to worry about inconsistency. But if tau square is moderate or large, it means there is important between study variation. What you will observe is that fixed effect model is narrow, but random effect model is a little wider, and the prediction interval is even wider. And depending, so remember when we say, well, imprecision is, we assess imprecision by the number of thresholds that being crossed by the confidence interval. You have to be aware is that you're using a random effect model. Some of this crossing may be due to inconsistency, not due to imprecision. And if you want to differentiate, you need to do fixed versus random analysis. But in a certain way, well, it really doesn't really matter from the decision making whether you're losing certainty for imprecision or for inconsistency. Maybe not. So another way of conceptualize this, if you really want to differentiate between imprecision and inconsistency, you should compare your confidence interval in fixed effect model versus random effect model and see whether you're losing levels because between study variation or random error. Or another pragmatic way is, look, we are going to analyze this together, and you can say we're losing 2 levels for the combined effect of imprecision and inconsistency. That is also a very valid option. And this is if you use random effect model. The prediction interval gives more weight to the certainty that originates from the between study variation. So probably is a better estimation of the true uncertainty. One word of caution that in order to estimate the prediction interval, you need at least 5 studies, probably more than 10. If you have 2 or 3 studies, your sample effectively is 2 or 3 people or 2 or 3 studies. So the estimation of tau square is probably very, 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 very uncertain. So probably the prediction interval would not be very meaningful. So in a way, in order to use prediction interval, you need a minimum number of studies. And what you see that you have a large number of studies is that prediction interval and random effect model confidence interval tend to converge, because the larger the larger the number of studies, the more reliable estimation of tau square and tend to be very similar. But if you have a small number of studies, prediction interval is not reliable. So that's important to consider. So yeah, so this is one important point that, so beyond that the basic or uncertain severity basic of imprecision and inconsistency, that when you're using random effect model, you have to remember that you're not longer measuring only imprecision, you're also measuring consistency on the same goal. And you can conceptualize that all the threshold you cross to fixed effect model is what you should assign to imprecision, and any additional threshold crossed by the random effect model over the fixed model is what you should assign to inconsistency. If you don't want to do this exercise, you can say random effect model, how many thresholds are crossed by the combined effect of inconsistency and imprecision. That is also fine. By addition, if you are using the prediction interval, which is a new tool, remember you need a relatively large number of studies, at least 5, probably 10 or more. And you can say that any additional threshold crossed by the prediction interval over the fixed effect confidence interval is what you'll be assigned to inconsistency. Because remember, fixed effect model imprecision, random, and prediction interval is what inconsistency add to imprecision. Again, you can say the prediction interval is crossing 2 thresholds. We're rating down the certainty errors by 2 levels by the combined effect of inconsistency and imprecision. That's also fine. One important consideration, especially when inconsistency, and this is something that we saw in the risk of bias assessment, and you will see in the indirectness assessment, is we say when you have high and low risk of bias study, and they are not congruent, so in different range, you should rate down the certainty of the evidence by risk of bias. The same way, if you have direct and indirect evidence, and they show you different effects, so for example, small and moderate, you should rate down the confidence, the certainty of the evidence. When they are concordant, so you have high risk of bias studies, and both is showing you, for example, trivial or no important effect, you shouldn't worry about risk of bias. You shouldn't worry about indirectness. This is the general principle for indirectness and risk of bias. But it's important that you take into account when, if you are using random effect model, which typically we use, those inconsistencies due to risk of bias or due to indirectness will be captured by the confidence interval or by the prediction interval. So this is a representation of what the confidence interval in random effect model may look like. In the first scenario, you see that the confidence interval is wider, and the why is wider because it's capturing the between study variation. And in the second scenario, is narrower. Why is narrower? Because it's not capturing the between variation. This figure is say, well, here you can rate down one level by inconsistency, or you can rate the same level by imprecision, but by risk of bias or indirectness. But this figure is meant to show that if you're rating by inconsistency, and this inconsistency is the cause of this inconsistency is risk of bias or indirectness, you should not rate down the same by the same underlying factor. So if you say, okay, I have an inconsistency in my meta-analysis, and go and analyze in the meta-analysis and realize that the source of this inconsistency is risk of bias, then you need to pick whether you want to rate down by risk of bias or by inconsistency or by the combined effect of those. But you cannot rate down twice by the same underlying factor. Another way to conceptualize this is, for example, in the top situation, you see that you don't know whether the effect is small or moderate. Only one threshold is being crossed. So you can rate down one level for risk of bias or this one level for by inconsistency. What is not appropriate probably is to rate down two levels for the combined effect, because only one threshold is being crossed. And in another way, you are not sure whether the effect is more moderate. You are not worried about trivial and important effect. You're not worried about large effect. So if we go back to our definition of the certainty of the evidence, this should lead us to lead us to relate down by one level rather than two. So it's very important. Inconsistency may originate from risk of bias, may originate from indirectness. If you're going to rate down by indirect risk of bias, do not rate again for inconsistency. Or the other way around, rate down by inconsistency and do not rate down by indirectness or risk of bias. An example of this. Let's try to apply this to, and this is one of my favorite Cochrane reviews because it's something that I cannot relate with. And this is something that was very popular at some point, whether you need to do this keto diet versus normal carb diet to lose weight. This is a meta-analysis, is a lot of studies, 37 randomized trials, more than 3,000 people analyzed. And there is two important considerations in this meta-analysis, which by looking at this, you see that there is if you look at the risk of bias assessment, you see that there's a lot of red dots, mainly because I think if I remember well, this was missing outcome data. I don't remember very well, missing outcome data. And the other thing, if you look at the bottom, is down there, but this I-square is 51%. So okay. So the result looks inconsistent by the I-square. But now we need to, and that is what I like this example. We need to, whether this is I-square is just statistical inconsistency or is meaningful inconsistency. Well, let's do that. So we will follow our process, the 4-step process. We will determine our threshold, determine the rating, what we are rating. We are going to evaluate the evidence and determine whether to rate down. Yeah. So these are the thresholds I'm using for this analysis. This is based on expert consensus. So people from nutrition says in order to a weight change to be meaningful, you need to lose at least 5% of your body weight. This is what they have agreed that is meaningful. And it's a very well accepted and used threshold. So we can see, okay, what is 5% of the baseline weight of people? And the baseline weight of people on average was around 100 kilos. So we can say, okay, we can define these thresholds. We're going to consider a trigger small effect 5 kilos, small moderate 10 kilos, and moderate large 20 kilos. These are my set of thresholds. If you have different threshold, you may have a different certainty assessment. This is because the certainty assessment is totally dependent on the threshold you choose. That is why it's important to make it explicit. But with this threshold, we see that the meta-analysis, the result of the meta-analysis is a reduction of 1 kilo extra with the keto diet. The confidence interval is entirely with the, so it's statistically significant. So it's entirely within the, but it's entirely within the trivial no important fact. So here you have a case with the, and also is what I like this example, you may conclude that the keto diet is more effective than the normal diet. But then you say, well, because it's statistically significant. But if you look at whether this difference is meaningful, it's not, because 1 kilo is well below the meaningful difference, which is 5 kilos. So we are going to be rating the certainty of no important effect. That will be our target of the certainty rate. So I will give you a bonus about study limitation because it's so prominent in this meta-analysis. We already discussed this in the previous session, but as a reminder, so it's important to assess whether the study limitation, or what are the study limitation using a structured approach, that better structured than unstructured. But then when we assess this, we need to assess whether it has this an impact on the result or not. So another way of saying, it's not enough to say that many study has issues. That's not enough. We need to see whether this issue reflects in a change in the meta-analysis or not. And in this case, it's very interesting because 27 randomized trials are considered a high risk of bias. So this amount for the 74% of the weight of the meta-analysis. And another way of thinking is three-fourths of the body of evidence is high risk of bias, and only have one-fourth that is low risk of bias. So this may prompt you in the past to rate down by risk of bias because many studies are high risk of bias. But just so one step is to assess the limitation, which is necessary. But the second step, which is also important, is to assess whether this limitation has an impact or not. And this, we need to compare high and low risk of bias through a sensitivity analysis. And the hypothesis typically is that high risk of bias size may overestimate the effect. It may be different in specific scenarios, but overall, high risk of bias size tend to overestimate the effect of interventions. Let's see where this hypothesis happen in our meta-analysis. And we can see that low risk of bias suggests no important effect, and high risk of bias suggests no important effect. So bias is not introducing anything meaningful to your interpretation of the evidence. Another way to, if you want more technical, bias is not an effect modificator of the meta-analysis. That's more technical language. More simple language, you're saying, look, high risk of bias suggests no important effect, low risk of bias suggests no important effect. So bias is not influencing my view of this evidence. So assessing the risk of bias, despite that most of the body of evidence coming from high risk of bias, not serious. How about inconsistency? Remember that we have I-square of 51%. That might have prompted you in the past to rate down by inconsistency. But if we go to zero range, and I just draw the range in the meta-analysis of for the 5 kilos, that you see that all the studies, every single of them suggests no important effect. So what you're seeing here, this I-square is a statistical inconsistency, but it's not true inconsistency, because probably, and there is reason for this, because you are estimating a continuous variable, you have a lot of power, that you don't have a lot of random error, you have a lot of precision. So even a small difference, which are not relevant, may appear relevant because the power of the analysis. But this is a good example of something that is statistically inconsistent, but not meaningful inconsistent. So assessment is not serious. So if you go through this analysis, body of evidence as randomized trial, stats, high certainty evidence, we analyze study limitations and inconsistency. You can do the rest. There is no serious inconsistency, no serious no serious concern about study limitation. And also, if you go back and we'll quickly review this. So remember that we evaluate imprecision by the number of thresholds being crossed by the confidence interval. Here you can see that despite being statistically significant, we are not crossing any threshold by the confidence interval, so we don't have any concern about imprecision. So this is really high certainty evidence that it's very interesting because if you see the results from the statistical significant perspective, you may get the idea that keto diet is better. But actually, if you do the grade assessment, you realize that this is high certainty evidence that keto diet is not superior to the balanced diet, which is a totally different interpretation what you might get from looking at statistical significance. Want to know more? The Gray Book. Many of the things we have discussed is covering here. Some of the things we have covered here, like the use of prediction interval, and this is still part of an evolving grade guidance that we probably is not ready yet, but probably will be in the future. And if we publish something new, the first place to look at it will be the grade books, because also one of the important features of the grade book, which is not here, is the grade map, which is a repository of all the updated paper. Grade has been around for 25 years. Some of the early papers are not longer considered updated because the thinking has evolved over the years. So if you want to access the latest version of grade, the grade book and the grade map are the best way to do it. Thank you, everyone. I invite you to follow us on LinkedIn, where we typically disseminate news and questions.
Yes, thank you very much, Ignacio. We have two questions in the chat. I think you can see them, but I will read them to you. Bernadetta asked, in relation to the previous webinar about study limitations, if all RCTs included in the meta-analysis provide no information on the methods of allocation sequence generation and allocation concealment, would you downgrade one level due to limitations in study design and execution? So what do you do if you don't have any information?
Yeah, that's a very good question. So I want to go back to my presentation. I'm going to go back to my, So one of the key, we told you the easy case, right? So you have high risk of bias and low risk of bias studies, and you can compare them. So yeah, that's the easy case, and I think the more straightforward. But the question that Bernadetta is doing, what happened if all the studies at a high risk of bias or unclear risk of bias? You don't have anything to compare with. That's a very good question. And in that case, rather than breaking down, because the natural response will be just write down. But rather than that, we are suggesting to make reasonable assumptions regarding, and this is more complex and probably will need a more explanation, but make reasonable assumptions about what the bias may be and see if this is plausible. So for example, in this case, you are so far away from your threshold. So because remember that our threshold was 5 kilos. And if you look at the confidence interval, it goes even, the farther you are is 1.5 kilos. So you're very far away from your threshold. So in this case, the amount of bias needed to see this result. So let's say the true value, believe that the question will be, will the true value be a small benefit for the keto diet? Then you have to be severely underestimating your effect estimate. In a way that is, so if you go to the meta-epidemiologic evidence, typically high risk of bias studies compared with low risk of bias studies tend to overestimate, so make the intervention look better by a 20-30%. So it's not very not a lot. This is an average, not a lot. But here, if you say, okay, how about the effect could be a 20 or 30% larger than what I'm seeing here, or smaller. You see, you make this assumption and you see there is still in trivial range. Even you can make the argument, okay, how about the effect was double or half? You are still on the trivial range. So in a way, you see that in order to get out of the trivial range, you need very extreme assumptions. So you have to be over or severely underestimating your evidence, which is not plausible anymore. So in this case, we believe even if all the studies will be high risk of bias, then you can make the case that you don't need to write down the certainty of the evidence. So in a way, trying to answer it, there will be more guidance coming about this. Rather than just writing down, we believe that it's better to make some assumptions about where the true effect may lie and see whether it is plausible, because many times you don't need to write down. So in a way, we're trying to what we're trying to avoid is to over-penalize the certainty of the evidence based on risk of bias, rather than whether you think that the bias is actually changing the result. This is still something that we haven't fully fleshed out. So it's a difficult case. It's not, but probably we will try to cover this with an upcoming great guidance.
Thanks, Ignacio. The next question is from Maria Angeles. How do you determine thresholds for areas where no MCIDs are available?
Very good question. So one important consideration is that threshold, they always has been there. So you always talk about small effect, large effect, small or important but not statistically significant, or statistically significant but not important. So there is always some quantification of the magnitude of the effect. What I'm saying is better to do this explicitly. So how do you do for dichotomous outcome? How do you do it for, we have an entire paper for you. And this is very good news, Maria Angeles, because I will suggest you to look at the grade, I will put in the chat, grade guidance 42, published relatively recently, when we summarize all the approaches. It's mostly, I think continuous outcome is covered on the paper, but most of the paper is devoted to dichotomous outcome. So there we can give you some ideas how you can elicit some threshold from your decision makers. So if you're working with a panel or you are working with a systematic review team, or if you want to calculate using average thresholds, we guide you cover there. We have some formulas for you to get some thresholds. So in a way, there is some ways to estimate thresholds. Even if your thresholds are not perfect, it's better to use it explicitly rather than implicitly, because one important thing about the grade is transparency. You may disagree with the thresholds, but at least you know in what you disagree. Because if you're not using threshold, then it's implicit. You disagree with the conclusion. You don't know why you're disagreeing with the conclusion.
Yeah, good point. Thanks, Ignacio. We also have a question from Jamie. Thank you.
Yeah.
Do you see the question?
Yeah, I see. Yeah. So this is so what is the thing? We have different ways to estimate the confidence interval. We have different ways to estimate tau square, right? So remember when we say there is, when you in the random effect model and the prediction interval, you're including tau square. And to calculate the confidence interval, different statistical method. And there are different statistical method to estimate tau square as well. So depending which specifically statistical method you use, you may find scenarios where one statistical method make you cross one threshold and another statistical method, and you are not crossing any threshold, or maybe not crossing one threshold. So that's something that may happen. We don't have an example, but theoretically can happen. And in general, we as a methodologist tend to be more conservative. So in a way to say, we tend to prefer methods which in a way show better the uncertainty of estimates. So another way, if our problem is to show uncertainty on the evidence, and we believe people is too confident making decision, and we should be aware of the uncertainty. So in a way, we tend to be conservative. So in answering your question, I prefer the HK method because give you a wider confidence interval. So another way to saying this is over the Dersimonian method, which is typically give you a narrower confidence interval. So if you have no imprecision and no inconsistency, use the HK model, then you're fine and you're more confident on your results. So in general, I would say I use that by default. You can argue that you can make sensitivity analysis with different statistical methods, but most of the time probably will give you the same answer. That's my guess. In general, I just don't do it. I use the more conservative approach, and the most conservative approach is the one that gives you the wider confidence interval. In this case, the HK method, and if you follow the latest Cochrane guidance for calculating t-square and the confidence interval, actually very conservative and give you a wider confidence interval. And in my view, this is a good thing, because if you're able to show a benefit with this wider confidence interval, then you are more confident in what you're doing.
Thanks. Thanks, Ignacio. The next question is from Kristen. How do we not the double downgrading? And you see her question in the chat.
Yeah. So the important thing is when you have inconsistencies, and this happens. So double rating is a very pervasive problem in grade. There is many scenarios because the domains of grade are a conceptualization of random and systematic errors, and they overlap. So sometimes it's not clear when one domain ends and when the other begins. In this case, in this specific case, if the reason for inconsistency is result bias or indirectness, you should rate one time for that factor, not two times. There is other, in a way, if you have a inconsistency and you explore your inconsistency and you realize this is because result bias, you may choose to rate down by result bias or by inconsistency, or you can break down one level by both. But you should not penalize the same thing twice, because the problem with that is if you use grade and always get very low certainty evidence, then you have a broken clock, right? Always tell you very low certainty, which is not really useful.
And in follow-up, question asked, which do you pick? Which do you report? Maybe is also an important question then. Do you have you say first you do study limitations and then maybe inconsistency, or?
It depends. I think it's the logic of grade start with so if you go to the grade, for example, grade prof software, you start with stability limitation, move to the but honestly, is the way I do it. Typically, I start with imprecision because it's easy to assess. So this is a very pragmatic way. If you already lose 3 level by imprecision, there is nowhere to left. There is nowhere to go. You already know it's very low certainty. So myself, I tend to start by imprecision inconsistent because to me they are easier to assess. But it's up to you. One important consideration is one thing is to assess the rating of the certainty, which is important, but also even if you are, for example, you have a very wide confidence interval, you lose 3 levels for imprecision. You may still want to assess result bias and directness because they may have implications for research, for example. But again, you know that you're already dealing with very low certainty of evidence. So it depends. If you want a quick assessment, you reserve very low. If you want a more detailed assessment, you can go to the other domain. I personally start for imprecision consistency because it's something you can see on the meta-analysis, but there is no way right or wrong. You can really depend how do you approach things. The important consideration is it's not right down by the same level, by the same issue twice.
Yes, and then clear documenting why you rate it down, right? And why you rate it down for study limitations and not so that it's clear for the reader.
Yeah, but I have an interesting question about RCT and this is, regarding imprecision in a review of the effect of calcium supplement in children's single RCT. The problem that I have is that I believe you're not capturing all the evidence, because we know that if you want to capture evidence about adverse event, you need to review non-randomized studies, because otherwise you're selecting a very small amount of evidence. So I will say that if you want to capture information about adverse event, you need non-randomized trial, because otherwise you will never capture enough information. But let's say there is nothing else. We have some rules for review information size. They are a bit more complex, because in a way, what you need to do is to do a sample size calculation and see whether you have enough information. For dichotomous outcome, like adverse event, we can have yes or no. Typically, 60 is well under the minimal review information size. So if you go to the precision paper, the grade number 35, there is even a calculator there on the appendix, and you can plug your numbers, and probably, given the review information size, you are very, very underpowered, and you should be penalizing the certainty of the evidence even by 3 levels in this case. So I will suggest to use that calculator, because there is some rules for that. I didn't explain because it's kind of more mathematical and complicated. But yes, when you have, in this case, if you have RCT with 60 events, by review information size, you're probably losing 3 levels of certainty of the evidence just by imprecision.
Thanks. And then the last question is from Jona, if I pronounce it correctly. Can you recommend us a correctly conducted systematic review with meta-analysis where the authors approach the risk of bias properly? And I think you're asking then for a concrete systematic review, like a reference.
Well, the thing is 2 things. So one thing is whether the assessment of the study limitation was done properly, and I would say most of the time it is. And I think what the more problematic is whether this leads to a rate down or not, which is typically people say a lot of limitation, we should rate down. Where we are arguing is, before doing that, try to see whether there is a difference between high and low risk bias. The systematic review that I just showed you about using keto diet versus normal diet, I think is a very well conducted review, very, very interesting, very good results. If you go to what the author says, they rating down 1 level by risk bias, which, if you think about it, is not so different from my assessment. The other thing that is very important is great about transparency. There is not inherently right or wrong rating. So I think, given what we know now, given the information we have, and we probably will write high, but moderate is also a perfectly reasonable conclusion. What is important is when the analysis is, you might disagree with the judgment, but at least you know what you disagree. So I will say, Cochrane reviews in general, the assessment of the risk of bias is typically well done. Then when you need to ask yourself, and this is a matter of judgment, whether you agree that how this assessment was reflecting the certainty of the evidence. And there may be legitimate disagreement in this, because you may have different perspective.